Welcome everybody to this video lesson. Today we're talking about concepts of simple harmonic motion. Let's start with idea of periodic simple harmonic motion. Let's just start with periodic motion first. So let's say you're dropping a ball. You have a ball, it just drops, comes back up, drops back, it keeps bouncing up and down. And let's say there's no energy loss, so it comes back to the same height. It repeats the motion periodically. We call that a periodic motion. You can also think about a clock's hand going back and forth, or a ferry wheel going back and forth like this in a rotatory motion. And if you analyze the motion of one particle, it's just going up and down, or going even round, and that's called periodic motion. Now let's talk about a simple harmonic motion. Certain objects, when they're going through a specific type of periodic motion, we call that simple harmonic motion. So let's say you have a spring here. This is attached on a desk like this, and let's say you grab this piece of mass that's attached to a spring. This spot over here, you can't really move it. You're going to pull this and let it go, and it's going to kind of go back and forth just like this, and it's going to stop at the end points, and it's going to go really fast at the middle. And this specific motion, if we call this simple harmonic motion, but what is it really? Let's explore that today. I'm going to start off by drawing this situation, and let's say initially we kind of have the mass over here, and then let's say this is at time 0, and then at 0.1 second, let's say it moves up a little bit, and then let's say at 0.2 seconds it's going to come to the middle point, and then a little bit later it's going to be compressed. It's going to be here, and then let's say at 0.4 seconds it kind of compresses fully and it comes to the top position. Now I've drawn this up to about 1.2, 1.3 seconds. And again, just looking at it right at the beginning, you pull it right over here. That's the end points, and it starts moving in this direction. At 0.1 second, it's here. At 0.2 seconds, it's right at this position over here. This position is the middle point over here. We call this the mean position, mean meaning average. And I'm going to label it right here. This is mean position. Another term that we use pretty often for this is equilibrium position. And this is again the average position of the particle. So it reaches here and then it starts moving in this direction. So we see it right about 0.3 second. It's here. At about 0.4 second, it reaches the top position here and it stops. And then it starts moving in the backward direction because the spring is really compressed at this situation, is pushing it back towards the equilibrium, and then the movement continues, and this is periodic. It keeps going up and down, up and down, up and down. And if I were to draw the position of this over time, we can see that it follows a line which looks like a sinusoidal graph. So it goes, continues like this, and if you let it go, this pattern continues for a very long time. Now, in terms of some terminologies here, the position of the object is always measured from the equilibrium position. So for example, the middle point or the mean position is here. So let's say I want to figure out where is it at time 0. The position is measured from here up to here. Let's say I want to figure out where is it at time of 0.5 seconds. Then the position is measured from the equilibrium position up to here, and that's displacement. Typically we use the letter X for this. Different curriculums might use different letters. Another important terminology is the amplitude, which is the maximum displacement of a particle or a system from the equilibrium position. So again, displacement is measured from the equilibrium position. The maximum distance that that particle or system is traveling is called the amplitude, and the symbol that we use for it is x naught with x with a subscript 0. The max amplitude can also be measured in both directions, so it could be here or here in this specific case. Now, as the particle is moving back and forth, every time it completes one entire trip, we call that a cycle. So in this specific case, it's at the bottom position. It moves upwards over time. It reaches the top position and it goes backwards and it reaches the bottom position. This is called one complete cycle. And the time it takes for one complete oscillation or cycle is called the period. In this specific case, we can measure the period from this position because that's the lowest position. It goes all the way to equilibrium, all the way to the top position, comes back through the equilibrium position and ends back to here. So this can be called the period. We can also measure it from the equilibrium position when it starts moving upwards all the way and then all the way back down to the very bottom and then all the way back to the equilibrium. As long as it's one oscillation, this is going to be a period. And we can measure the period in this specific case, and we know that at time 0 all the way to this position, 0.8 is the time it takes for the oscillation, so the period is 0.8 seconds. Alternatively, we can look at this position, which is 1, and subtract it by 0.2 seconds, and we can see that's still 0.8 seconds. Now, the idea of frequency is the number of oscillations per unit time. We can find this simply by dividing the number of oscillations by the time it takes. Or another way of doing it is to write it as frequency is equal to 1 over the period. For example, in this specific case, we have our period as 0.8 seconds, and this will end up giving us 1.25. The unit, whenever you write the number of cycles per second, ends up being hertz, and that's Hz, capital H, lowercase z is the letter that we use. So in terms of the definition, we often don't say number of oscillation per seconds because that would be the idea of what is the unit hertz, but in frequency it's just number of oscillation per unit time because it could be expressed in different units. Now, 1.25 hertz here means that every second we have about 1.25 oscillations. So we can see that here we had about 1, and you can see that if going from the amplitude to the equilibrium position takes about 0.2 seconds or a quarter of a period. So we have one whole period plus a quarter of a period in one whole second, and that's where the 1.25 hertz comes from. The one last idea before we move on from ideas of periodic simple harmonic motion is the fact that in this specific case, we're kind of making an assumption that there's no heat loss or there's no energy loss in the system. So whenever we have when we move the particle down here, it started oscillating back and forth, but it's not losing any energy, because if it was losing energy over time, the displacement of the particle or the amplitude will reduce, and we'll start getting the particle kind of stop back at the equilibrium position or end up at the equilibrium position. We are making that big assumption. Let's talk about position, velocity, and phase. Initially at time 0, we have displaced the object to this point over here. Let's say that's in the downward position. So that's displacement over here. We're going to have up to be positive, so I'm going to add that to this diagram. So up is positive and down is negative. So my position at the very beginning is in the downward direction. Let's say it's right here. I'm going to put a point right there. And at 0.2 seconds, it reaches the equilibrium position. 0.4 second, it goes to the amplitude in the upward direction. Amplitude at equilibrium at 0.6, amplitude at 0.8 in the negative direction. So I can put all those points in. And again, at 1 second, it reaches the equilibrium position. At 1.2, it reaches the amplitude in the upward direction again. And I can draw a sinusoidal curve here showing how the position of the object changes with respect to time, the position of the particle or the position of the object. And again, we are assuming that there is no energy loss here. Now let's look at velocity. So when we get it to this point over here, at this point over here, it's not really moving. So if I were to write its velocity, it would be 0. The spring is fully stretched, so it's going to put a force in the upward direction, pulling this in this, pulling the object, so its velocity is going to be in the upward direction. Right at the middle point, the spring is no longer it's no longer compressed or stretched. So at that point, it puts no force, but the object has a lot of momentum moving in the upward direction. So it's going to have a high velocity in the upward direction. And then as it's moving upwards in this direction, the spring is becoming compressed. And when it's becoming compressed, it's putting a force in the downward direction. Now the object is moving upwards, but experiencing an acceleration or a net force in the downward direction, meaning that it's going to slow down. So it's not going to change direction yet, but it will go slower. And at some point, it will get to 0 point. And at that point, we have a maximum amount of compression on the spring, meaning it's going to put a lot of force in the downward direction, meaning it's going to start pulling the object in the downward direction. It's got 0 velocity, so it's going to accelerate this way, and therefore it's going to have a velocity in this direction. That acceleration continues. It's not a constant acceleration. It's a reducing acceleration as the spring stretches. But at this point, it's going to have its highest velocity going downwards. Once it passes the equilibrium position, the force acting from the spring, now the spring is stretched. And when it's stretched, it's going to be pulling the object downwards. In the upward direction. And when it does, the object is moving down, but experiencing an acceleration in the upward direction, and therefore is slowing down, so its velocity reduces. At some point, it reaches a 0 velocity, and again, the object now the spring is fully stretched, meaning it's going to exert a force in the upward direction, and the object will start moving, so it's going to accelerate a little bit, and it's going to speed up just a little bit. At this point over here, the object is moving in the upward direction. The spring is stretched, meaning it's going to be pulling the object in the upward direction. So it's moving up, velocity is up, acceleration is up, and therefore it's going to be speeding up. So when it reaches here, it's going to have its maximum velocity. And then right when it passes the equilibrium position again, the spring is now compressed. And when it's compressed, it's going to be having a net force on the object in the downward direction. Object is moving up, experiencing a downward acceleration, meaning that it's going to slow down. And then it's going to reach 0, and that pattern continues afterwards. All right, so now that we kind of have an idea about the velocity of the object, a phase is the position and velocity of a particle at any point. This is what we call the state of the object. So at this point, for example, its position is at the amplitude in the negative direction, or the negative displacement here. So that's its position is a negative displacement here, and its velocity is 0. And at this point over here, this position is 0. It's right at the equilibrium position, and it's got maximum velocity in the upward direction. When we say 2 points are in phase, it means that they have the identical position and velocity. That would mean that, for example, at this point over here, the object has position of negative amplitude, because it's in the negative direction. We're taking up to be positive. It's got zero velocity, and this point doesn't have the same position, not the same position, not the same position, not the same position. We go back at this position, it's the same position, and it's got the same velocity. So these 2 points over here are in phase. Any two positions which have different positions and velocity are out of phase. So basically, if they're not in phase, they're out of phase. These two positions, these two positions, these two positions. So anything that's not these two are out of phase. For this specific points, this and this point, so at time 0.1 second and 0.9 seconds, we have the same position and velocity, so they're in phase, but all of these points will be out of phase with the particle at 0.1 second and the particle at 0.9 seconds. There's a special case for out of phase, which is called opposite phase, and that's when the particles are half a cycle or half an oscillation apart. So for example, at time 0, the particle kind of moves in one whole oscillation up to 0.8 seconds. So half a cycle or half an oscillation apart is 0.4 seconds. So the particle at 0 and 0.4 seconds is half a cycle apart, and therefore they are in opposite phases. So anytime particles are about a cycle apart or one oscillation apart, they're in phase. It could be 2 cycles, 3 cycles, 4 cycles, because they always go to the same position and velocity. And half a cycle, 1.5 cycle, 2.5 cycle, there will be in opposite phases. So for example, here with the 0 and 0.4 seconds, remember that 0.4 and 1.2 seconds are in phase. So that would mean that 0 and 1.2 seconds are also opposite phases. Phases are used mostly to compare two different waves, so we'll get to more details about it in future videos. Now let's get into more details about concepts of position, velocity, and acceleration for an object undergoing this periodic motion, which we call simple harmonic motion. So we have a spring over here. This time I've kind of flipped the direction, so it's moving right and left, and we're gonna label the right direction here to be the positive displacement, and anytime it goes to the left of our equilibrium position, we're going to call it the negative displacement. So basically for our position, we're going to take right to be positive. In terms of velocity, whenever it's moving to the right, it doesn't matter where it is, as long as it's moving to the right, it's going to be positive, and anytime it's moving to the left, we're going to call it negative. Same thing for acceleration. If the acceleration is towards the right, we call it positive, and when it's towards the left, we're going to call it negative. Also note that position is the only one that even if the object is moving to the left, but it's in the right side of the equilibrium position, it's still in the positive direction, and that's very, very important. So let's draw a free body diagram of the object at every single point. So at the very first position over here, the object first of all is in the positive x direction, and it's in the positive amplitude. So I'm going to say positive max. So it's in the max displacement towards the right. Its velocity is 0 because it's not moving at that specific point. And in terms of the forces, the spring here is fully stretched, meaning the spring is going to be pulling the object towards the left, and it's a pretty large force because the spring is fully stretched. And therefore, because the net force acting on the object is in the left direction, it means that acceleration is also in the left direction, meaning that it's negative, and it's quite large force at this point, so large acceleration as well, so it's negative max. At the next position over here, we have the, and we can also label these on the diagram as well. So initially the position is at the max position, and then we got our velocity, which is 0, and we got our acceleration, which is negative max. So I'm going to label it right here. At 0.1 seconds, we can see that our object, the force, well, it's moved a little bit, so the spring is not as stretched anymore. So the force is going to be slightly smaller at this position, meaning the acceleration is going to be negative, but it's not going to be as large. It's still displaced to the right of the equilibrium position, so I'm going to use positive. And velocity, well, it's moving to the left, so velocity here is going to be negative. Now at this point over here, it's reached the equilibrium position. Force, there's no forces acting on it at the moment because the spring is neither stretched or compressed, and therefore it's not pushing it in this direction, it's not pulling it in this direction. So really there's no forces acting on it, or net force really. The position is at the equilibrium position, so the position is going to be 0. Velocity, it's moving to the left at the moment, and there's no acceleration on it either. So I can add those points. That's at quarter of a cycle. We got the position is now at 0. We got the velocity, which is negative, and we got the acceleration, which is 0. Then a little bit later, so first of all here, it's accelerating this way, moving in this direction, so it's speeding up. It gets faster in this position, moving to the left. It's super fast here, but at this point over here, or any time that it's moving in this direction, the force acting on it is actually to the right because the spring is now stretched. So the force is going to be this way, and therefore the acceleration is going to be positive at this point. The displacement, well, now it's to the left of the equilibrium position, so I'm going to put negative here. And velocity, well, it's moving to the left, so I'm going to put it as negative at the moment. Next section, we got the spring is now fully compressed, meaning it's going to put a large force in this direction, meaning we're going to have a very large acceleration. So I'm going to say positive and max. Velocity, well, at this point it has reached a 0 velocity, and the displacement is still negative because it's in the negative side of the equilibrium position. I can put those positions on my diagram, remember, so we are now a half a cycle or half an oscillation apart, so displacement is negative. We got velocity, which at the end position is now 0, and acceleration is max in the positive direction, or in the direction to the right. Now the object is at rest over here, but there's a force acting to the right, meaning it's going to start moving to the right. It's not going to be super fast yet, but it's going to be moving to the right, so it's going to have a positive velocity. It's still in the negative direction or negative side of the equilibrium position, so position is going to be negative. The force acting on it is smaller because the spring is not as compressed, therefore we have positive acceleration. Direction is to the right because the net force is to the right, but it's not as much. A little bit later on, there's no force acting on it because again the spring is neither stretched or compressed. The displacement is 0, acceleration therefore is 0, and the object is still moving to the right, so it's going to have a positive sign over here, and we're going to add that to our diagram. So 0 and 0 for velocities and position, acceleration and position, and velocity here is going to be positive because it's moving to the right. Finally, for the last 2 points, we have our object is now in the right side of the equilibrium position in both of these cases, so I'm going to put positive for both. In terms of forces, it's now the spring is stretched, so it's pulling in this direction, and as the spring stretches more and more, the force acting on it becomes more and more. So the acceleration is going to be negative, and at this point is the negative max. So it's a very large negative force, net force, which causes a very large negative acceleration. Velocity, well, the object in this point is actually still moving to the right and it stops here. So zero velocity here and it's still moving to the right at this position. Let's draw the last points here. So acceleration negative, we got velocity, which is now 0, and displacement, which is positive. And I can draw this. Again, it follows a sinusoidal function, and it looks something like this for the first cycle. The velocity time looks something like this. And acceleration will look something like this. And just to check our fundamental understanding from the kinematics unit, we got a position time graph here, and the slope of a tangent here should always represent the velocity. So the slope here is a flat slope, so flat line here, meaning the slope is 0, meaning velocity should be 0. Slope here is very negative, meaning velocity should be negative. The slope here is 0, meaning that velocity should be 0. Slope here is very positive, velocity is positive, and slope is 0, and velocity is 0. The slope of velocity time graph should represent acceleration. We got a very negative slope right here, representing a negative acceleration. We got 0 slope, we got positive slope, 0 slope, and we got a negative slope on the velocity time graph, which means we got negative acceleration. The other part that I want you folks to pay attention to is the idea that if you look at the position time graph and the acceleration time graph, they look similar but in the opposite direction. So it's mirrored around the t-axis over here. It doesn't mean that they have the same values, but the shape has flipped on the t-axis. Okay, so we've talked about periodic motion, and many objects may behave as periodic motion, but what does it mean to undergo a simple harmonic motion? Well, simple harmonic motion is a motion that explains many phenomena in the world. For example, a ferry wheel moving around in a circle. If we track a vertical position or horizontal position of any particle or any person sitting in there, it will follow this specific sinusoidal motion. Other examples include things such as a pendulum. When it's oscillating in a very small angle, we'll talk more about it later, it oscillates in what we call simple harmonic motion. Or if you have a tuning forks which are oscillating, it's often the particles in it often behave the same way. Now, the motion or the idea here is if you look at the force acting on the particle, if you look at this force diagram, you can see that anytime the position is in the positive direction, the acceleration is in the negative direction, always pointing towards this equilibrium position. So positive points towards the equilibrium. When position is 0, acceleration is 0, and as soon as the position moves in the negative direction, the force changes towards the equilibrium again. So one idea of simple harmonic motion is that the acceleration or the net force always points towards the equilibrium position. The other condition for simple harmonic motion is the idea that as the displacement increases, the acceleration or the magnitude of acceleration or the net force also increases. This is much easier to see when you have a spring, because you know that for a spring, as it stretches more and more, the force also increases. So as the displacement from the equilibrium position increases, the magnitude of the force is always increasing, and therefore, because F net is equal to mass times acceleration in this specific case, As net force increases, the acceleration also increases. So the two main conditions for simple harmonic motion is one, that acceleration is always pointing towards the equilibrium position, and two, the acceleration is proportional to the displacement of the object from the equilibrium position. And let's do the math for this a little bit. So we know that based on this idea, acceleration is proportional to x, but the direction is always in the negative direction. And if you remember from the force of a spring, we know that F net is also proportional to the acceleration. So F net in this case will be proportional to negative x. And we know that for the net force and then this specific spring is actually equal to the spring force. So this is going to be proportional to negative x. And if you remember, if something is proportional, it could be expressed as the equation of mx. And this is where we get the negative kx from, where x is the displacement from, or deformation really, or displacement from the equilibrium position, and k is the spring constant. Another way of writing this equation, I'm just going to write it here, since acceleration is proportional to negative x. We'll go over this equation in another video, but acceleration will equal to some sort of constant multiplied by the displacement. And this constant is actually omega squared, which is 2 pi over the period. And what this means is that if the object is going very, 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 very slow, meaning it has a large period, it would mean that this value is going to be very small and the acceleration is small, which kind of makes sense. It doesn't need to accelerate as much if it's going slow. But if the period is small, meaning this value is very small and this is going to be very large, acceleration required to keep that oscillation or period is going to be a lot larger. The very last idea I'm going to cover is the idea of how does acceleration and velocity vary with the displacement of the object undergoing simple harmonic motion. So we know in terms of position, if the position is positive, we get a negative acceleration. So if we want to draw that, we know that when you have a positive displacement, you get a negative acceleration, and vice versa, when you have a negative displacement, you get a positive acceleration. So here we have this, and we also know that acceleration is proportional to negative x, meaning that I can draw a line of best fit which is straight and it goes through the equilibrium position, and that shows the acceleration relative to the displacement, meaning that whenever the object is in the negative position, for example here, it's experiencing a very high acceleration towards the right positive direction, and as the displacement decreases, that value of acceleration decreases as well. And this would mean that the acceleration is not constant in a simple harmonic motion. In terms of velocity, well, whenever the position are in the maximum positions, velocities are 0. So I can put those in. Velocity is 0 here, velocity is 0 here. And whenever we are at the equilibrium position, we could have a velocity which is in the negative direction and very large. And we could have a velocity which is positive and it's very large. So I can put a point here and I can put a point here. Note that the acceleration is really, really, really large at these points. So the velocity changes very rapidly at this point, but the velocity doesn't change nearly as rapidly when it gets to this point over here. So that would mean that initially it changes quite a bit, but it slows down. And if we continue this, it will look like an ellipse. And these are the graphs of velocity and acceleration with respect to the displacement of the objects. Okay, we covered a lot of ideas and concepts about simple harmonic motion for kinematics. We're also going to make another video on energy and how does that change with respect to time and position. We're also going to have another video for equations of position, velocity, and acceleration with respect to time. And we'll have another set of videos for spring equations and pendulum equations. I hope you enjoyed the video. Stay tuned for the next ones.